Now here I circle, so from here link to the same solvent that you use, but different reagent NaCl. So the same thing, nucleophilic sub, replacing the Cl with the Cn here. So now we have a new function group called nitrile, right? Now, layman terms, this is also commonly known as step-up reactions because there's a gain increase by 1 carbon, right? Now then over here, you can undergo 2 more useful reactions, subjecting the nitrile to acid medium, right? Then you change the Cn to COH. We don't really have to take care of the N, but like Lashita, she wanted to write out what happens to N. The N actually become ammonia, which will further react with the medium, the acidic medium, to give you ammonium NH4+. But that one not really important, Okay, so what you want to enhance, you can enhance with this one here. For example, okay, acid hydroxy. So what are the, the actual reagent? You can use any dilute acid like HCl, H2SO4. Okay, that's all they keep lah. Any dilute acid will do. Okay. Now then after that, if you want to subject nitrile to reduction using agent, you can. So this one type of for you already. Basically, again, focus on the one in blue, C triple bond N. The C triple bond N becomes CH2NH2. You just gain hydrogen, put it across C and N. If you see I color code, right, then you become clearer. Because that's how I think also. Gain of hydrogen, right? That's part of the features of reduction, right? Yeah. So from the C and N, I just add a H across. Okay, that's all. Okay, okay. Now I got some more information over here. That one I probably will talk more when we move on to carboxylic OPCMA. For example, here acid hydrolysis, right? We can actually subject nitrile to this reaction, right? Actually, we still have another 2 more functions that can undergo the same reaction. Namely, ester and amide. But this one no need take down, just for your information only. Okay, we will venture into it later, much later. Okay, and then last but not least, all right.
Which
amide? This is amide.
Oh, okay.
Amide look almost like ester. Just the ester you have an O here. This is NH2, things like that. We will look at it later on. Okay, now I'll move on to this one first. Last but not least, the excess concentrated ammonia in ethanol heat in seal tube. Okay, well, you don't have to use ammonia. You can use any look alike, right? That your amine also can. Okay, yeah. So then after that, do take note that why do we need to use the new profile in excess? Because you want to keep the substitution only one time. You do not want this product, right, to continue to react with any excess halogen alkane. So we want to keep halogen alkane limiting reagent. So nucleophile must be excess, things like that. Okay, so this I think is good for you to take down. Not new, just take down. And function is another nucleophile. What do I write nucleophilic? Nucleophile.
I remember writing this down somewhere. I don't remember where.
You know, OPCMA, confirm OPCMA.
Which OPCMA?
What chapter is it?
Oh, okay.
That's why I miss it. Or when I come here to teach, right? I cannot.
I drew out some more here.
Yeah. Well, good that at least at the back of your mind you remember you had it somewhere, right? Lashita, do you remember writing it somewhere? Because I didn't see for 3 months according to you say, but I just saw them like in December, so I have like 3 weeks, right? Yeah, 3 weeks. 3 weeks versus 3 months. There's a huge difference.
I said that November, like
I know. So do you fly somewhere to where? Do you go somewhere? No. Why? If you miss opportunity in December last year, June you can't go anywhere. June is like legit the only time that you can study, right?
No, my parents are like, finish your A levels first. Yeah, finish your A levels and then.
They don't think them say yes, can save money. Then you go a big one, a major one in
I
December.
hope, fingers crossed.
But you already went to US last year, right?
Yeah.
Yeah, so actually very far already.
Yeah,
Where
so-
where do you want to go?
Yeah. I mean, that one is like must do. Cause like, you know, like how Indians we have to like do certain things for like the
So we
my-
did it religious purpose?
no, it's like for relatives.
Oh, okay,
It's like
okay.
my mom's younger brother, so like must do ma.
Ah,
And like we didn't see like, cause I have a cousin, I didn't see him ever since he was born. So like
so the
it's
way
been like 8 years
like,
since,
oh, baby, then who?
actually because yeah, like almost 10 years since he went. So like yeah, must go ma.
I see, I see. Or maybe next time can go Europe lor. That is the
Best.
because you go Europe probably will be minimum I think 2 weeks I think because you take so long to fly there then you come back 1 week I think waste of time. Right?
Can you convince my parents?
I think if they don't need any convincing, you know, because you all didn't go anywhere in June, probably they plan something major, really major. Yeah. Okay, all done?
Mm.
Okay, this is on reactions, right? Now then I'm gonna give you another worksheet where I put you to test on whether you can recall. No need to recall, I can refer, okay, whether you can refer correctly the mechanism between S and
SM1, SM2.
correct.
That's okay, that's okay.
So you want me to push out a little bit, or you want to change place? You want to shift up here? Go first class seat.
First class, this is the first row.
Do it like that. No, first class because you always your look will always be the first one which I can. Not true. I don't know what stressful lah. Just me, I'm not done yet. Go, do it. Go and look through the cheater one, look through my one, don't look at that. Okay, come. Okay, I put this on for a while. For those who are done, right? You can work on this table of comparison, okay? For you to compare SM1 and SM2. So it gives you an incentive for you to read through the mechanism first. Okay. Okay, this one, question one, okay? Now let's go through this one. Okay, question one is you need to use Aries OPCMM as well, okay? Now, correlate the presence of element chloride. May I know what role does AlCl3 play? Anyone can contribute, doesn't have to be the
Yes.
Lewis acid, Bronsted acid, halogen carrier, catalyst, all here. Okay. Now, for example, halogen carrier, I think that's quite straightforward, right? So because you can see from the generation equation. Ooh, wait, okay. At the end, it takes up the extra Cl, so that's why it's called a halogen carrier. Catalyst because at the end of the reaction, it's being regenerated. Okay. Then Lewis acid is from the lone pair perspective, right? Where it take up the lone pair. Okay. So things like that. Okay. Now, so in this case here, the first part will be right. When you subject react with this, okay, so we have one chloroethyl benzene, which is one here, right? React with ICl, the presence of this one here. May I know what is the electrophile that it generated? This one react with this one, what does it create? Plus AlCl3. So you want to help me out here? That's my step one, right? Generations of your electrophile. What electrophile? Is it two options? Option one, I plus. Option two, Cl plus. Which one?
Cl.
I plus. Why?
Cl.
Because if you look at it, you draw the ICL bond, right? Someone can help me continue my explanation? Why at the end you have I plus?
Cl is more electronegative. The electrons are pulled to Cl.
Very good. This is Cl is more electronegative, which make your I more electropositive. You know, instead of talking about, or can say less electronegative lah. So therefore, it should be the polarity should be as such over here. Okay. So at the end, right, when you subtract this to this, then next one will be your Aldene. Okay. Look at this. Do you think it's 2-4 directing or is it 3 directing? So just go back to your Aries opposite again. How do you tell? Look at your pre-existing group. If your pre-existing group contain bare only single bond, it should be 2-4 directing. If you have double bond, multiple bond, it should be 3 directing, right? So you go back to the questions here, it's all single bond. So therefore your electrophile here is either attached to the second position or the fourth position. Am I right? So therefore your product here it can be here or here, right? It can even be on top here as well, right? Okay. So then after that, you subject this product here to aqueous sodium hydroxide. The reflux over here, it just means the apparatus you use, that's all, right? So the second step over here is your nucleophilic substitution with OH minus. So your job is to tell me which CX bond is weak enough to be broken. That's all. This one can or not? Can you break the CCl bond here? Can you undergo substitution basically? Then how about the I that attach directly to your benzene ring? Why not? Lachita, why not?
No, but how though? It can't like directly go there.
Huh? Why you cannot cleave this CI bond here?
It's like super unreactive. Then
Wait.
Benzene can undergo electrophilic sub, but can it undergo nucleophilic sub? Why no?
it's like
It is no BCM. It is.
No, because the double bonds make it
Are you sure it's allergic of double bond?
Isn't it your electron? Wait.
But it's not a double bond. It's not a double bond. It's a triple bond.
The pi electron system attracts electrophile, non-electrophile.
Okay, there's two reasons. Now, one of the reasons actually you got it in terms of this is electron rich, right? So definitely this carbon here will not be electron deficient, basically. So it will not attract electrophile. But the actual reason I give you, I printed, I think it's not that reason.
Okay.
I give you another reason that, a more common reason that can be looked out for. So you want to help me out here? Why from here, as long as the halogen is attached directly to the benzene ring, it will never ever be broken? Why?
reactive.
Why? I know it's unreactive. Carry on, continue. I draw the lone pair for you. So the lone pair on the halogen atom delocalize into the adjacent benzene, resulting in no. Okay, very good. It's not legit a double bond, it's a partial double bond, it's 1.5. Right? So anyway, 1.5 is still stronger than single bond, right? So that make it NPFP. And I'm very hard to see. So it's over here. Alright?
Totally remember, yeah.
Yes, but then just now you say double bond, but here I got the partial that.
Partial the actual benzene ring itself.
Actually, actual benzene we also don't have a double bond, it's partial 1.5, okay, because of the resonance going on. So at the end here, right, how do I choose? I definitely have to choose such that I, right, regardless of whether it's further to the second position or fourth position, it will still be there. Yeah. So it's C. Now, okay, ready, all done, Okay, let's move on. Okay, question 2. Okay, one more of P undergoes reaction with this. This one, the moment you see this, right, you will undergo this thing called elimination, right? It gives you these 2 moles of HBr. What does it mean? It means that there is 2 HX bond that you can eliminate it, right? Okay. Let's take a look at the first one, A. For A, right, how many HBr bonds we extracted out? Can I start with nitric first? For option A, if I subject this A to this reagent, how many byproduct HBr do you take out? One, very good. One is this H here, one Br here, one H here. So only one HBr that you managed to remove, right? Okay. Okay, next one. For option B, can I have a Matthew? How many HBr can you eliminate?
0.
0.
Why?
Why? This carbon adjacent to this carbon is this carbon, right? This carbon got H or not? No H, right? Then how to do elimination? Right? Okay, so 0 HBr. So your turn. Can you help me do C and D together? You do C first. How many HBr can you eliminate? 2, okay? One is, for example, I can do like that. The other one is one here. Then there's another H here as well, right? Adjacent, right? Okay, so there's 2. How about the last one? You thought it's 2 as well, right? Is it? Then I've got 2 answers left. So maybe Matthew and Logita can help me take a look at option D because some of you feel that D also 2 more, right?
Is it 0?
Why now change to 0?
Is it 1?
You feel that it's 1. Can I have a 0? You want to explain to me why is it 1 and why is it 0?
The carbon adjacent to the carbons bonded to the bromine has no H.
Okay,
yes.
Look at this Br, right? This carbon here, adjacent to this carbon is this carbon. Do we have a H now? So it's 0 now. Okay?
Yeah.
So what's the thought process? You look at the Br first, you see where the Br attached to. So adjacent to this carbon, which is this one, right? Got H or not? No H. Cannot have any elimination there.
Then why the other side? No.
This one,
No, this one.
this one.
Option D, this left side.
Okay, this Br is attached to this carbon, right? So adjacent to this carbon is which carbon? This one again, right?
Oh,
Still no H.
okay.
Okay.
Why B?
Huh? Why B also no, is it? Okay. This Br is attached to this carbon, right? And what is the adjacent carbon relative to this carbon? This one, right? So this carbon got any H or not? No more H because each carbon in the benzene ring is sp. Wait, no. sp. If it's sp3, then you have 4 bonds. sp2. So you can only have one thing attached out, that's all. The moment you have something there, right, there's no more H already. Fair enough? Fair enough. Okay. So answer is B or C. I mean C. Okay?
We didn't put the BR the one top.
Which one?
The one on top.
A, huh?
The one B, but BR that is correct.
This one is A. Okay. This carbon, right? This carbon is this carbon, right? Correct now. Okay. Yeah, this carbon does have a H itself. But the thing is, right, do benzene ring want to do elimination? Because the moment I do elimination, you destroy the resonance structure. Right? So probably you will never do so.
But why is it elimination for this one?
Ethanol.
Because it's ethanolic. That's what. Okay. Okay, let's move on. So the moment you do ethanolic, then the OH minus will function more like a base rather than a nucleophile. So it extract the H itself. Okay, the actual mechanism of elimination is not in your syllabus. Okay, next one, question 7. Okay, 4 drops of 1 chloro, 1 bromo, 1 iodine was put separately into this. Okay, ethanolic silver nitrate. I think someone asked me, is it you? They asked me what does this do. This one work exactly the same as this. If you look at OPCMF, right, the one I've given you is in a 2-step manner. Step 1, we will add in your aqueous sodium hydroxide heat, right? Then after that, we add excess HNO3 in a way together with silver nitrate, right? So these two, right, work the same as this. I didn't give you this one because not all JC teach student this one here. Okay, so just know that this one here has the same effect of bringing up the halogens so they become halides and then allow it to form PBT with the respective silver ions, things like that.
Fair.
Okay, so the rate was in the order. Why is this so? The rate, assuming concentration stay the same, for drop reactor concentration is exactly the same, right? So then it will depend on the bond. Okay, so what's the answer then? D, that's all.
You got one correct.
Very good. Okay, so can see our 4 drops of same concentration. Okay, let's move on. Question 8. Over here. Okay, 2,2-dimethyl propyl, which is this one. Okay, can be synthesized in the following reactions here. Okay, KCl, remember, is a step-up reaction. So this is a step-up. Okay, by 1 carbon over here. All right. So what you can do is, right, recognize this. So it work backward. CH2NH2, when you convert back here, it should be CH3, then C with a CH3 and then C triple bond N. Understand? Remember just now we did the flow chart? So now I'm facing backward. Then after that, your E, just replace C triple bond N with any of the halogen. So which one does it look like? Did I make a mistake here? CH3, I think doesn't this is typo, is it? CH3. Oh no, not this one. Oh, CH3. I think it's A. I think it's A, right? It's A, right?
Yeah.
Right?
At least I got A.
Yeah. It's A. Okay. Bracket just means it's bonded to. So basically this carbon is bonded to 2 methyl group, which is this one here, and then 1 halogen alkene. That's all.
Okay.
That's how you can read it. Can